I'm Phanish Puranam. In this short video, I'd like to talk to you about some reasons why you, as a scholar who studies organizations or management, might want to consider the use of models as a technique as part of your research portfolio. There are a couple of additional readings that you might want to take a look at as well as a complement to the topics we discuss in this video. So why do we model at all? Why not just write our theories and our arguments in natural language, in English, or in some other language for that matter? The fact is that formal languages, like whether it's mathematics or graphics or algorithms or a programming language, they have features that make checking internal consistency much easier than natural languages. That's really the main reason why we use formal languages, formal models, to try and capture our theoretical arguments more precisely. In particular, I tend to think of it as a crutch for cognition. It's a way in which we can improve the quality of our thinking beyond what we would do naturally without these formal languages and models. And in particular, it helps in three ways. Firstly, it makes our arguments more precise. Natural language sometimes can have inbuilt ambiguities. It can help understand interactions between things, which can get quite complicated and very difficult to verbally discuss or explain to people. And finally, it can help with dynamics, which is another form of interaction, but over time. So how variables in the model interact with each other over time can sometimes become very difficult to keep track of, particularly if there are multiple variables involved and they also interact in interesting ways. So I'll give you quickly some examples of each of these benefits. Here's example one. Here's a statement which can be completed in two ways. Firms are bundles of heterogeneous resources, or firms are heterogeneous bundles of resources. Very similar wording, but it makes a big difference because only one of these statements is necessary to explain inter-firm differences in performance within an industry. That's the basic question in strategy, right? And if you think about it for a bit, you'll probably figure it out. But if you wrote it out as two different algebraic expressions, it would be very obvious that in fact, it's only the second statement that is necessary to explain inter-firm differences, not the first. Here's another example, slightly more complicated. We know that trust and detailed contracts are just two ways, among possibly others, of supporting collaboration between people, between organizations, between different divisions, between different parts of two large companies and so on. Now, each can magnify the benefits of the other. So trust and contract can be complementary. But you can also get two kinds of crowding out effects. If I write a detailed contract, maybe I'm signaling that I don't trust you. The other way in which you can create some crowding out effect is that trust may just build up more slowly in a situation where there is a detailed contract. So when I see you being nice to me, I can't tell if it's because you're trustworthy in general or you're doing it because the contract forces you to do it. Given these three possible ways in which the two interact, should we observe a positive or a negative relationship between the ex-ante trust and the extent of detail in the contract that firms choose when they enter in a relationship? This is actually quite an important topic which scholars who study strategic alliances and contracting have been tackling for a long time. But it turns out that the answer to this question, do we see a positive or a negative relationship, actually depends on a crucial premise. Is the extent of detail in the contract being chosen in a maximizing way, or is it being chosen in a matching or a satisficing way? Right? And this is an argument that Bart Bannister and I developed and published in a paper in 2009. And just to give you an extract from that paper, it shows you all the possible shapes of the relationships between ex-ante trust and the level of the governance complexity, the contractual detail that you may actually see in the relationship. And as you can see, the relationship can have very different shapes depending on whether you go with the matching approach, satisficing approach, the first column, or the maximizing approach, the second one. Third example, here's a stylized fact. Firms, unlike humans, tend to actually have a lower risk of dying as they get older. Okay, so they're less likely to die as they get older, as opposed to us unfortunate humans. Now, here's one story. Maybe this is because they're becoming better at what they do. Here's another. You don't need that story, the first one. You'd get the same result if, in fact, firm performance at any point is just random, and firms die when cumulative performance falls below zero. Right? It's a pure selection kind of an effect going on. So here, notice that what's happening here is that a new story, story 2, which involves interactions and dynamics over time, is being proposed as an alternative explanation to the simpler story 1, which is only superficially simple because it actually makes lots of assumptions about learning, competence, and performance, and so on. But story 2 is a simpler explanation if it were true. So how do we know if it's true? We can model it, and this is exactly what Dan Leventhal did in a very famous 1991 paper, where we can replicate the results in this paper very easily. And if you do it, what you see is that mortality risk actually declines over time if just those two properties that I discussed earlier were true, that performance in any period is random, and if cumulative performance falls below 0, you go bust. Now, when we talk about formal models, broadly it's helpful to think about two classes of these. So the first are what we might call agent-based models. These are models in which the central actors in the model, or the central entities in the model, are individual agents who behave according to certain decision rules. So each agent is making a choice in every period about what to do, and those choices then aggregate up to define the performance of the system. In economics, game theoretic models are agent-based models. We could have computational agent-based models, which are much more common in organizations. The contrast to that are aggregate property models, which describe the performance of the entire system comprising multiple agents perhaps, but in aggregate terms. So it gives the relationships between variables rather than relationships between agents, which is the first approach. So in economics, a lot of macroeconomic models are of this form, and in organizations, systems dynamics models exactly have this flavor. Another distinction that as a new modeler you might encounter and want to think a little bit about is the difference between models that produce proofs versus those which are essentially read through graphs. Now, in the proofs kind of a model, what's going on is, given a desired result, we want to think about what kind of reasonable assumptions and some kind of a solution concept, often involving equilibrium or stability or optimization, which is some combination of these, what will yield the result that we want. And the spirit is very much one of reverse engineering. So we know the final result, we want to figure out a model that produces that outcome. The simulation approach is different. It starts the other way. It says, given reasonable assumptions, how does the system behave over time? Can we observe the pattern, and then can we explain the pattern? So the spirit is much more, you could think of it as prototyping, where we're trying to build the model to capture some essential aspects of reality, play with it, see how the system behaves, and in the process learn about what's actually going on here. So which is better? It's a false debate in many ways, at least in my mind. Proofs are always better if you can get them. Okay, this is the problem. Many organizational systems are not very easy to characterize in a way that proofs become feasible. And in my view, at least, it would be quite absurd to change the problem just in order to get proofs. So we want to capture real phenomena, and if in doing so we struggle to get proofs, then simulations are fine. Now, what do I mean by saying proofs are not possible? Possible for me, or possible for somebody else, or possible for a better mathematician. And there is some truth to that. One way to approach this is to invest in the tools that help you do proofs when they're possible, or you trust in the division of labor. You could focus on doing the science, explaining the phenomenon, understanding what's going on, and hope somebody with better math will come along and do the proofs at some point. But all I'm saying is there is space for both kinds of play in the models that we work with. To wrap up, if you want to become a good modeler, there are some basic skills that you will need to develop. Perhaps the most important is actually a qualitative one, which is how to abstract from reality in a sensible way. Then there are some mechanical skills around deriving insights from the model and evaluating the model against evidence. And finally, there is a accumulated wisdom kind of a skill, which is just knowing a large family of types of models, so that you have a patchwork of these models in your mind. And when you look at a new problem, you know which one goes with which one. So let me close by leaving you with a very interesting and inspirational quotation about modeling, and think about whether this is the right tool for you and for your work. Thank you.